All right. Welcome, everyone, to the robotics seminar. Happy to introduce Kostas Bekris, who is an associate professor at Rutgers. He has done a wide span of work in robotics and is going to be talking about some of the key challenges that we still have that I believe many of you have also, one way or another, looked into tackling from the aspects of perception and Sim2Real. I got to interact with Kostas through Amazon. So Kostas is an Amazon scholar and has been since 2019. And so you all know the scale at which Amazon operates at and the level of reliability at which we need robotics and all the challenges therein. So we very much look forward to what you have to share with us today.
Thank you for the kind introduction. Welcome everyone, and I'll be talking about two areas that I believe where we need to put a lot more effort to make progress with the deployment of robots in the real world. Kind of two gaps between perception and planning, as well as Sim2Real. And I think most of you and most of us in robotics these days were all part of this effort to transition our field from the traditional setup of high volume manufacturing, where the traditional objectives are high speed, accuracy, and consistency of the repeated tasks. And we want to put robots into the field, and we want to put robots into our homes. And I think the current commercial applications that attract quite a bit of interest, autonomous driving and logistics, are stepping stones that we have to solve if we want to go eventually into the field or the jungle that our homes are for robots. And especially in the case of logistics, that I have been doing some work over the last few years, I think if e-commerce was not a big business by itself, roboticists should have discovered it to make progress with robotics. It introduces some of the complexity that we may face in service robotics. There is a very large variety of objects that you may have to manipulate, for instance. At the same time, it is a little bit easier. There is some structure. You may see objects on a conveyor belt. So we kind of get access to a lot of data these days and the ability to build systems that perhaps eventually will go to much more unstructured setups. And I was inspired to get into logistics because back in 2015 there was the Amazon picking challenge. It was posed as a competition for the academic community. We have to pick items from these shelves that they're very dark. You see that they're actually kind of metallic. And given the 6-7 months that we had available to put together a system, we went with the textbook approach. We're going to sense, we're going to plan, and we're going to act, and then we're going to cross our fingers, and everything is going to go well. And what can go wrong, right, with sense, plan, act? Well, everything can go wrong. Perception may not return you the correct answers. There is noise. Your planning may not discover solutions when they actually exist. Your execution may be erroneous. So we have to think here how we put those components together. And some of the questions are, what is the right representation that perception can build reliably in a fast manner so as to have kind of a more closed loop operation that is informative enough for the planner to be able to come up with the right choices. Very frequently, even if you try to follow an approach for planning that takes into account the fact that there may be noise and uncertainty, if you do some form of planning under uncertainty, we tend to make convenient but unrealistic assumptions. For instance, I know where all of the objects are. It's just a Gaussian around my estimate that perhaps introduces some noise, and then I can solve the system reliably. But perception does not necessarily fail in these nice ways. You may not see a big part of the scene. You may see phantom objects and situations like this. And I think some of the important things that we should be pushing forwards are tighter closed loop operation between the two, kind of streaming continuously data from perception, and a planner that adapts and also has fallback plans every time that we believe that we do not have sufficient amount of information to react. And we shouldn't forget about robotics hardware as well. I mentioned that these Amazon shelves were metallic. We were also using a kind of a big metallic robotic hand gripper at the time. We were injuring ourselves all the time because of these choices. Compliance is something that can be very helpful from the hardware side, right? And it can introduce some safety as well as adaptation to failures at the mechanical level. So I'm collaborating with Aaron Dollar at Yale, and he has been building for many years adaptive under-actuated hands, and he has converted me into this line of thinking, that compliance is your friend. For instance, these hands kind of adapt to the shape of objects without you have to reason too much about how to manipulate the fingers. At the same time, every time that we transition to these kind of softer, more compliant mechanisms, we lose something as well, the predictability of rigid mechanisms. So there is, more uncertainty in this setup. So it's much more difficult to precisely model. And we need those models to kind of, either apply some of the classical techniques on the planning and control side, or even if you are a big supporter of, machine learning and reinforcement learning, typically in this domain, RL will also be very data hungry, and you will benefit from a simulator where you can train first on the simulator and then transfer it back to the real system. But if you do not have an accurate enough simulator for something like a soft robot, how you can actually be able to come up with a method, for a complex behavior. So, the second type of gap is, the simulation to reality gap that I'm going to talk about. We have done some modeling work for adaptive hands, but I will actually use a different compliant mechanism in the second part of the talk, which comes from the area of tensegrity, robotics, and for locomotion challenges. So let me first focus in the case of trying to close the gap between perception and planning in the context of robot manipulation. And I have to warn you, the only sensing input that we are going to use here is RGBD data. We're not going to use tactile sensors or haptic information. And it's not that I don't believe that it's useful. It's kind of, in terms of limitations on research bandwidth, we have focused primarily our expertise on being operating over RGBD data. But we're also going to try to use compliance from the side of the mechanism whenever possible. And I'll use some use cases of what we have tried to do in terms of manipulation tasks and how we developed perception techniques and used planning solutions on top of them as well. And the first case study is this robot packing problem that a company, an e-commerce company, posed 3 or 4 years ago, JD.com, where we had an unstructured pile as the start configuration for our objects. We did have access to models for these objects, and we need to tightly pack them into a new destination bin. And this introduces, you have to sense what happens in the picking configuration, and you also have to be careful at your placement scene so as to achieve a desired configuration. This motivated us, and especially after the Amazon Picking Challenge, we got much more into perception solutions for trying to figure out the pose of objects that we need to manipulate. Specifically in this domain, one of the challenges is that you have a lot of similar objects and many instances of the same object in these dense, unstructured piles. So we tried to come up with solutions for solving these challenges. And again, one of the limitations in this context and with 6D pose estimation is that you do not necessarily get labeled data in a very cheap manner from at least in the real world. Actually, after the Amazon Picking Challenge, I asked one of my students to put together a data set, which is now known as the Rutgers APC, the Rutgers Amazon Picking Challenge data set for 6D pose estimation. He put a lot of effort over that summer to measuring the position of objects and orientation of objects inside the Amazon shelves so as to have ground truth information. And then he gave up the PhD because he said, if that's what I'm going to be doing with research, it's not very exciting. It's a very useful data set. You should use it, though. Now, so we went into this domain of trying to come up with pose estimates for the objects. And some of the challenges here is that because they're very similar, you kind of need to understand where are the boundaries of them, and we didn't want to go into any such painful labeling process. So we're big supporters of trying to train as much as possible in simulation. So we trained in simulation where label data are available. But then you have to close, the Sim2Real gap in terms of the perception side of things. So we get a lot of labeled data in simulation where we know the semantic segmentation, we can come up with the boundaries, and then a lot of examples of real scenes that we want to apply at this domain. And through an adversarial learning process, we can actually close the gap so to be able to make predictions also on the real images that are trustworthy. So we have in the end, in the gun here, we have a domain classifier that is trying to distinguish whether your input image is actually real or not. And we have the generator that actually makes the predictions in terms of the classes and the boundary. And we want to confuse the classifier at the end so that you do not know if it comes from real data or artificial data. And this increases the accuracy of the prediction here without ever needing labels for the real data. And we do this, over these images. We come with pose hypotheses for each individual object in terms of their 3D pose. We are learning how to score them and to say how accurate each prediction is. And then we also operate at the scene level and try to introduce some knowledge about the physics of such scenes. So pose hypotheses that are consistent should not result into interpenetrations between the objects. So for each object, we'd come up with a hypothesis, and then we come up with an optimization solution of what is the best placement for the objects that do not violate physics. And it's kind of consistent for the entire scene that we get. So we use this as input into our process now for performing a manipulation, and we use just a suction gripper, which, by the way, I tell to Aaron Dollar that he's the expert on compliant end effectors, that suction grippers are a great example of compliance, and he gets very upset with me. He gets disappointed with me as a collaborator. But actually, suction grippers, they are soft. There is, you can push a little bit towards objects, and it's not going to destroy your scene. I think it is an example of where compliance helps in this case as well. And our first attempt was, okay, we need to pack the items in a target bin. I'll sense at the pick scene using the technique I told you, which comes up with very good estimates for poses. I'm going to pick the objects. I'm going then to just place them directly where they need to be at the target bin to achieve packing. And of course, what can go wrong with sense, plan, act? Many things are going wrong, even in this setup, where we really pushed on high accuracy perception. So what can happen is that you may want to place, for instance, the objects on this, let's say, the larger support area of those soaps. And what the object looks like in the pick scene, what it gets exposed is the other orientation, like the shorter area. And with the suction gripper, you do not have dexterous manipulation capabilities. You cannot easily reorient the object before placing it. So how are you going to place it with the desired orientation when you pick it with the opposite orientation? But that's where you can actually use the environment as an additional finger, thinking in terms of the lines of Matt Mason's and Alberto's kind of thinking. You could actually topple objects inside the pick scenes just with your suction gripper. And it turns out actually having a compliant base for the environment allows this toppling operation to work much more reliably. So we start introducing these kind of planning fallback solutions every time that we face a problem, right, in our pipeline. When we actually place the objects, we never go exactly at the location where we want the object to appear. We try to go somewhere emptier in the environment and push towards this target location. This is a much more robust operation, which also packs the objects that have already been placed there. And you may still fail and sometimes place an object on top of other ones. Your poor suction gripper is also a very good finger to push things and try to bring them all at the same level. And our students did a lot of experiments in terms of ablation of how these methods, these components can help you with the quality of the output of the packing process. So, with toppling, adaptive pushing, and corrective operations. So this baseline is using just sense, plan, act. So pick from the orientation and place it. You may get very unstructured piles at the end, as unstructured as you started with, so no victory. This shows a case where we do have adaptive pushing and corrective operations, but no toppling. So you see that they're kind of nicely packed, but not all objects have been transferred into the target scene because not the right side of the object is available. Without adaptive pushing, we brought all of the objects, but the scene again looks quite unstructured. And without no corrective operations, we have quite a bit of gaps as well sometimes between these objects, and it's kind of this refining that is used to then get consistently experiments where we pack the objects effectively. And you can see here a video. This is a setup now. We have two types of objects. We have these Colgate toothpaste and these Dove soaps. So the perception, first this is tasked to detect where the Colgate is and then pack it. And then we're going to go towards the Dove soap. We showed at some point the one next. This is 5x that's happening now. And interestingly, for the Dove soap, one of the reviewers, I think in our paper, told us, well, you've shown a lot of examples where you place the Dove soap on the stable surface, the large one. What if you have to place it actually in the short surface? So we did some tests, and here we're actually going to be placing them onto the smaller surface. And we're lucky for some of the objects in this situation in the beginning that they're also exposing this small surface, so we don't have to do any toppling. And we place them in the target area, and you can see the adaptive pushing. We go a little bit off, and then we push every time towards the other objects. And the next pick is actually going to be a situation, I think, where we pick an object not from the right orientation, and we also have to perform some toppling, right? And it's going to find an empty area at the bottom of the pick scene, and then reorient it, kind of raise it in this situation, and being able then to expose the right side and then do pick and place, still with adaptive pushing. This pick failed, right? It was not very nicely aligned. The next one is aligned. If you're using suction cups, use a lot of flow to try to pick as much as possible items in the scene. So in this setup, we kind of have these fallback plans that help us a little bit to adapt to situations where kind of the happy path may not work. At the same time, our sensing is very snapshot based. We kind of observe what is happening in the pick scene. We observe the place scene. We figure out if something went wrong. But manipulation is a much more dynamic process. And I mentioned the compliance of the suction grippers. When you pick something, objects move quite a bit, especially with the adaptive hands as well that we're using from Aaron's group. Because they are compliant, you do not have very good forward kinematics to know exactly where the object that you pick is located. So if you want to place it now in a tight area, you want to have an idea of the pose of the object at the time of the placement. And as you place, you may have contacts, right? And what happens now with the pose of the object during the contact? What if I want to do insertion in a tight area? So we need to keep track of the poses of these objects actually much more dynamically. So we first focus in the setup where we do manipulate objects, and they are actually picked by adaptive hands. And we went with situations where there is significant occlusion of the object. There is actually a manipulated object in this situation inside the adaptive hand, and it's a textureless object that is hidden quite a bit relative to the static single RGBD camera viewpoint that we have. And we come up with ways to kind of initialize a pose estimate for where the object is, where we simultaneously detect the hand configuration from vision in order to inform us about the configuration of the picked object. And here we assume, for the time being, that we do have access to object models. Eventually, we're also going to waive this. So we come up with an initialization for the object that has been picked after the grasp by something like an adaptive hand or perhaps a suction gripper. Right? And now we're going to be manipulating it. For instance, here we show a manipulation where you can see a little bit the motion as well of the object after being manipulated by the gripper. We're going to do things like passing it to a parallel gripper, and we want to place it into a tight area. So we focus now on developing tracking mechanisms where we can quickly update our estimates about the object location. And you can see that this is actually an output on some existing data sets from computer vision, where we're aiming either under occlusions to be able to still keep track the pose of objects. So how do we do that? Again, we want to train, first of all, with simulated data that hopefully will transfer well into the real world. The idea is that online, during inference, you're going to have RGB data at every time step. You're going to be making an estimate about your object's pose. And then you're going to generate simulated images of how your object looks like in terms of the RGB image and the depth image from simulation, given your current pose estimate. And this represents your belief right now. So how your simulation, according to your pose estimate, tells you that the world looks like. Then you get a real image for the next time step. And we're inserting now into a neural network the real image of the current scene with a simulated image from the previous scene. And we're trying to come up with a difference in the pose for the object. Right? And the idea is that by accumulating these differences in poses, you're going to keep track of where the object is. Now, why do we use as one input the real scene and the other input the simulated guess about how the object looked like at the previous step? Because we want to reduce the gap between training and testing. In training, we only use simulated data. So both sources of input are simulated images. Now, you jump into the real world, you should use the real image for the latest scene, but you can keep at least the previous scene, you can generate simulated data, and now you have a smaller gap in terms of what you do during training and what you do during testing. And again, the type of training data that we use, right? You go into Blender and you move objects and you have ground truth information and you can train this process. Now, anyone here doing kind of state estimation should perhaps complain about this approach that we're making guesses about the change in the pose. If you have a consistent error in these guesses, this over time, you are going to have drift, and you're going to start deviating from the correct path. It turns out that here we have good enough estimations, and the algorithm runs fast enough that the motion of the object is relatively small, that we didn't even need to do anything about drift. But I will get back into this point. So, we did experiments on some of the benchmarks, and here these graphs on the y-axis is the accuracy. And, the higher, the better. It's a different metric that we use for taking into account the symmetry of objects or not. And on the x-axis is the computation time. And the more to the right you are, the better it is. It's frame per second. So you want to be on the top right, which is where we are, and you see the alternative methods. My student working on this, Bowen Wen, he told me he runs at 90 hertz. I was not believing him. It runs very fast as an approach. And the benefit is kind of, it comes down to a neural network call during online inference. And once we had that, this became kind of an unblock again for us for doing manipulation. So went back and talked with Aaron. We were trying to do this insertion task with adaptive hands. So we had, openings that were sub-millimeter bigger than a peg that we wanted to insert. And that's a traditional challenge, right, for dexterous manipulation. So what we're doing, in order to try to solve this problem, we use now our visual tracking, where we have very high frequency estimates of the object's pose. So this continuously getting streamed. And Andrew Morgan, Aaron's student, who's actually, I think, on the job market this year, had built this learned strategy of what should be the controls applied to the finger so as to apply a desired change in pose in the object, regardless of the object. They basically reason about the triangle defined by the contact points between the three fingers and the object. So they know if you want to change it by a delta x in pose, they come up with the controls on the fingers that will apply this change in the pose for the three contact points in the plane that they define. So they had learned that they were getting poses from our visual tracking system, and then they kind of came up with the typical high-level strategy that we typically perform as humans for inserting objects inside tight openings. You kind of want to touch first the side of the opening, kind of tilt the object and insert it, right, in order to succeed. So we were trying then to move the object so as to follow this kind of high-level plan by observing where the object is and where it should be. And this allowed us to start solving these problems for a variety of objects. So these are kind of standard shapes. You see the predictions of the visual tracker while this is being executed, and we're using the adaptive hand to perform the operation. And again, you see it's 3x, 5x, depending on the object, the video here. But the opening also is, again, sub-millimeter bigger than the actual object. And we were interested to evaluate what is the most critical aspect of this system, because it brings together multiple things. You have a compliant hand, and Aaron's argument was, well, it's the compliance, stupid, right? That's what solves the problem, right? It's my hands, right? And there are other arguments here as well. Is the fact that you have this closed loop operation and the fast response from the controller because you have the fast visual tracking. Or it's the fact that the vision is accurate enough that you can solve this problem, and if you had more erroneous measurements, you would also not be able to solve it. So we did this ablation. This is, for this type of objects that we tried in our experiments, kind of the success rate over experiments. And then on the right-hand side, it's a table with a number of successes where first we reduced the level of compliance on the system. So the experiments that I showed before were executed at Yale with a compliant arm, compliant hand, and kind of a compliant base for the receptacle. And at Rutgers, we repeated that by removing compliance from the system. Right? What if we have a rigid arm? What if we have a rigid hand? What if the environment is also rigid? And as you remove compliance, the success rate goes down. Right? So compliance does help to increase the success rate. Right? So Aaron has a point here. The other thing we did was kind of slow down the reaction of how frequently we update and we move the object relative to our observations. And I think predictably, this is the one that has the most kind of catastrophic result. We go from our close to 10 out of 12 successes to very quickly going down to 0 if we are slower at updating the poses, or if we try to do an open loop control where, okay, I guessed how I picked it in the beginning, I assume it's going to remain constant during the whole operation, and then I just follow my plan. It doesn't work. And then in terms of adding noise into our vision output, we also have degradation in performance, right? And at a certain level, if your vision estimates are noisy enough, this is not going to work. We've also tried with the kind of more open world examples. Again, kind of this kind of packing situations, but much more tighter this time. The marker insertion is the one that Bowen was telling me is the toughest one. Very few point cloud elements here. Again, very tight setup. But you can actually, have correct solutions in terms of achieving insertion in these setups.
Possible architectures for your SE3 tracking. Is there a reason, is there any intuition for why you like the sort of pose refinement setup? Is there something about that worked particularly well?
It's very simple, and I have to say I didn't like it myself. Bowen persuaded me that this is I thought it wouldn't work because that we would see drift. But the predictions of the network, trained with the labels from simulation, we first tried it switching from simulated data directly to real data, previous scene and next scene, and it was also having high error. As soon as he switched to getting one of the images to be simulated, the error was small enough, and we were not seeing kind of increase in drift. And the fact that it's just a network makes it also fast, and how much you have moved at the next step, you are still in the vicinity of the previous estimate, so things are working nicely there. But we do need for generating the simulated scenes as training, we need to train over the models, right? So we do need models. So our next objective was, what can we do in domains that we do not know the object model beforehand, that we need to manipulate? And can we actually, and in this situation, a drift does become a problem because the estimates for the relative transform for the objects is larger, and you have to deal with it. So the setup is, let's say that we have an unknown object, right? This is the master bottle from YCB database, but let's say you do not have access to it. How can I still keep track of it? First of all, pose estimation for unknown object models is kind of a little bit of an ill-posed problem. What does pose mean if I don't have a model of the system? The best thing that you can come up with is relative transforms between frames. So you can say that if I have a segmentation of the mask in the initial scene that tells me this is the point cloud that I'm interested in tracking, I'm going to give you estimates of how this point cloud moves between consecutive frames. Now, if for the first frame you have some way of coming up with a global transform relative to a frame that you're interested in figuring out the position of the object, then you can just compose and then know also the pose of the object everywhere. Right? But otherwise, because I do not have a model, we cannot really talk about pose in a global frame. All right, so how did we try to solve this problem? The first part of the pipeline is kind of similar to what I described you before. It's a neural network that is going to come up with an estimate of the change in the pose between consecutive snapshots of the object. Right? We cannot use simulation now here as input to the image because we do not have the object model, so we're not going to be able to hallucinate it in this way. So we're using real images as inputs. We used pre-trained networks, and you may be able to do better with more recent architectures these days. First, for coming up with a segmentation of where the object is on each image, and then for detecting key points on the corresponding masks. And once we have the key points on the previous and the current snapshot, by matching key points, we can come up with an initial guess of how the object has moved between two consecutive frames. But this is very erroneous guess in this case. The error relative to the previous setup, where we could train simulation with a simulated models and have access to model of the object, is much higher. But how do you reduce your uncertainty? Well, we take the ideas kind of from the SLAM literature. Let's use post-graph optimization to improve our guess. Let's introduce our initial guess for where the object is in the last frame as part of this post-graph where nodes corresponds to different viewpoints of the object during the manipulation trajectory, and not just recent ones. We actually have a way of selecting the previous viewpoints that will actually give you similar views of the object. So as to have features that are similar to what you're seeing now. And then you come up with terms here, like pairwise terms that say, given the feature matching between these two viewpoints, that's my guess for the relative transform. We also do ICP, and we also get another term in terms of the point cloud to give you an idea of the constraint between pairs of nodes in these two different viewpoints. We optimize. Bowen did it on CUDA. It's fast enough, and that was one of my worries, that post-graph optimization would be slow, but it's fast enough to kind of do it online. And now you're able to get a better estimate for your latest frame and potentially also correct previous frames, right? And you go back and change your estimates for the past object poses. And then you select whether the last frame should also participate into your memory pool, where in your memory pool you actually want to have very diverse viewpoints of the object. So, for any new scene, you need to be able to come up with features that are going to be matched. So this is, the first part, come up with a guess given two snapshots. The second part is kind of globally optimized given all of your viewpoints and update your representation for that object. And it turns out to work, very well. It's not as fast as SC3 TrackNet, the previous approach that uses models. It runs at 10 hertz instead of 90, and you can see a little bit the breakdown between the different components like segmentation and post-graph optimization. It performs significantly better relative to other approaches that do not have any idea of the object model, and on par with methods that do have access to category level models. And this is kind of the error over time, over trajectories. the drift doesn't show up. Basically, because we're doing post-graph optimization, we can and match older viewpoints with the latest viewpoint. It actually keeps the error lower. So here are some results. The ground truth is going to be down here at the bottom left, and the bottom center is you're going to see bundle track running, and you're going to see some competitive approaches. And it's also very stable as a result, which is also very good, again, for manipulation, to have these jumps in the estimates in your tracking. This is a data set that we have released where we actually manipulate objects with a suction gripper that I showed before, and we try to place it into a constrained area. Ground truth now is at the top left. This is 1x, and bundle track is at the bottom right. And you see some of the other alternatives where they can lose the object because at some point you see a very small side of the object, very few point cloud elements, and there's not too much information there. But bundle track does a good job of keeping track of it. And that was, again, kind of another unblock for us to go back into manipulation problems. But when interned at Intrinsic, and Stefan Schall's team at the time, so we were trying to see if this would make sense in some of their objectives. And one of their tasks was, could they achieve transferring information from a single human demonstration on how to perform a manipulation task to solving the same problem with a robot. So I'll run the video here on the right. This is a different type of gear that is being manipulated by the robot that has not been seen before. And it's trying to match the demonstration trajectory from an object in the same category. And you see its execution. So we're trying to kind of clone this trajectory, although you're actually going to be executing into a different instance from the same category. So how does this work? This is kind of the high-level system pipeline. I'm sure it's overwhelming. Let me try a little bit to decipher what is happening here. Well, first, we're going to have this demonstration video as input, right? And things are going to be executed online. And we're going to use this tracker that I just described without knowledge of object models in both situations, both to track how the objects get manipulated by the person, as well as how it's going to be manipulated by the robot. Now, the challenge is now how we're going to be transforming the demonstrated trajectory that the tracker returns to where the new object should be, given the changes in shape between the two objects. So we have to kind of have a way of mapping a trajectory within the category. So the choice that we have to come up with is how to think about this mapping. And for this person, we are using a representation we refer to as non-uniform NOx. NOx, I think it was proposed by Shuran and Leo Gibas's groups, corresponds to normalized object coordinate space that kind of describes a six-dimensional space, position, and orientation for the category of objects that basically tell you how to kind of change the if I observe a point cloud for one object and I observe a point cloud for another object, it can give you the poses of these objects from different instances in the same category in kind of a common frame. Well, we tried to use NOx directly, the six-dimensional representation. It was not solving the problem for us. We actually had to introduce also scale and went from a six-dimensional representation to a nine-dimensional representation, and that's where the non-uniform part of the name comes from. So how do we train this representation? We have example models of, let's say, gears from the category, for which we have kind of the ground truth pose of these objects. And we see, partial point clouds of them in the different poses. So we can kind of map them from the partial point cloud to this 9D space that best matches between them. Then during the testing stage and the demonstration, you're going to see one of the shapes that you have actually trained with, and you're going to kind of come up with a complete guess of where this object is during the demonstration. And you're going to see a gear that you have not seen before. And given the partial point cloud, you're going to be making a guess about its 6D pose and scale in the same common space. And now you want basically to map the trajectory of the new object so as to follow as close as possible in this 9-dimensional space that is common in the category. And you want to kind of follow the trajectory. So the first thing that we tried is, OK, let's follow the trajectory, put a coordinate system for one of your demonstrated object at the center of mass, put it also at the center of mass for your target object. But in this situation, this mapping you need to come up with the right frame of reference for performing the mapping between these two spaces. When we just set it at the center of mass, what happens is that because of the change of the shape, you may get collisions. We are able to transfer kind of the trajectory from the demonstrated object to the new one, but this doesn't mean that we're not going to collide with the object. If we follow kind of Russ's work on K-PAM and try to pick a static key point, but not necessarily in a very intelligent way, we may also have failures. For instance, we picked the key point to be the center of the pole of the battery. And we kept it static throughout this process. This also results in some cases in collisions with kind of the environment. So instead, we try to come up with a dynamic way of coming up with these key points that allows that they move during the trajectory. So we compute a sign distance field for our object, and we kind of move the key point to be the closest point between your object that is kind of being inserted towards the receptacle area. And it actually moves during this process and adapts and jumps, to first at the kind of the center and then at the bottom of the one pole of the battery. And this doesn't kind of need human annotation, and at least for this family of tasks, I'm not arguing that this can solve any task, but this kind of insertion tasks, it is good enough to come up with the frame of reference on how to map the demonstration trajectory to the target trajectory. So you can see here some examples where we just demonstrated for one battery, right? That was part of our CAD models, and now this is executed into different batteries that we had not seen during the training. And it's actually the same canonical trajectory. You see kind of the same type of behavior that is being applied to all of these batteries. So the second part, I don't know how I'm doing time, is a little bit smaller. So, but let me know if you have any questions in this context of tracking 6D poses and manipulating.
So when you map the trajectory, are you like per time step in the demonstrated trajectory, mapping like each action that corresponds to wherever your current time step is on the execution?
So I was really excited to work on this part of and I thought that's my time where we're going to do planning and control, and it's going to be something really sophisticated that's going to solve the problem. And Bowen told me, no, yeah, I just follow the next point on the trajectory, and it works. And I was like, how could it be? It ended up we're doing, it's called follow the carrot following. So the next point that is the closest to where you are right now.
Where you are now. So
yes.
If something unexpected happens, you could still like look
you
up
could
the time.
You could jump somewhere.
Or jump back
yeah,
if you need
yeah.
to.
So it's a very simple strategy. I spent like 2 weeks coming up, suggesting to him, no, you need an intelligent controller, and that worked. Any other questions? So I have been using in this line of work, adaptive hands and soft adaptive hands. Let me talk to you about another compliant mechanism that we have been working with, and it's not in manipulation, in the manipulation domain. It's we're primarily using it for kind of locomotion strategies. And I learned about this type of robots through NASA collaborators, which have built this Tensegrity robot. It's if you think in terms of its surface, it's an icosahedron. It has 6 rods and 24 cables. It's a high control space system, and they're excited about it because it can navigate over uneven terrain. And it's, again, another example where compliance can help you to deal with some real-world challenges. And they had developed NASA simulators that it's possible to kind of train there and kind of practice with this system. So I was really excited. Most of my background is, motion planning and planning, especially for systems with significant dynamics. And I said, we have asymptotically optimal kinodynamic planners. We're going to use them, in their simulator, and we're going to solve some of the problems they cannot solve. And in simulation, we did a good job. We were able to show that we could come up for this complex system with trajectories where the tensegrity would be able to go over an obstacle, so it would contract its height in order to get to a goal on the other side. Kind of search-based approaches where you have kind of a finite number of primitives that you can use may not give you enough variety of motion primitives to solve this kind of problems. And we're also able to navigate over uneven terrains. It doesn't show very well here, but this is an uneven terrain. Here you see that we come up using sampling-based planners, the type of strategies that allow the tensegrity to go under this horizontal obstacle. All right, so in simulation, we're able to come up with controls for these complex systems. And we tried, to now transfer these planning solutions onto the real platform at NASA Ames. And it was not working. First of all, these planners think about the entire state of the system, and they need this as input. And what the real platform has, we may know its initial state, but then you only have IMU input at every point in time, and that's what you have as information to work with. At the same time, Sergey Levin and Peter Abil, they had built the guided policy search as one of RL approach for coming up with controls, and they did apply it successfully on tensegrity platforms. They were able to generate at least this motion behavior, where the tensegrity is able to move forward on a straight line as a wheel. They call it wheel rolling. Right? So there are learned this specific behavior. Then we said, OK, that's great. Well, let's build on top of that and try to come up with more complex behaviors. And we faced kind of a data efficiency problem of the RL strategy. We needed, it seemed that we needed a lot of data to try to come up with more complex behaviors. So that's where actually our planners came to be useful. Instead of starting with the RL kind of bootstrapped with random controls and try to come up with a new behavior, we used the output of our planners in simulation to come up with more complex behaviors. This is the wheel rolling when you try to give it kind of waypoints that are not on the line. You're actually not going to be able to follow a strategy. And this is the output of a controller that we generated using still guided policy search, but first bootstrapping it with solutions from our planner, and then also reasoning a little bit about the symmetry of the platform and kind of, instead of thinking about the global pose of the system in simulation, reasoning about its support triangle. And basically what you do with this tensegrity, you have 3 points that you touch the ground. And if you move the center of mass of this platform outside your support triangle, you're falling into a new support triangle. And you could think in terms of the coordinate system of the support triangle, and that's what your controller needs to be doing. So so this had a reduction in the space, by an order of 20 times a smaller space, or 24, given the symmetry of the system. And the fact that we're bootstrapping with planning solutions, we could come up with more complex behaviors. So we were very happy. We were now able to, in simulation, come up with these kind of trajectories over uneven terrains. So these spheres here are goals for the tensegrity, and as long as the center of mass ends up inside one of these spheres, we declare it as victory, and we are coming with the controls. And actually here, this solution is not using the global state of the tensegrity. It's actually using simulated IMU data, so the kind of data that the real platform has. So this works with the real type of sensing information. But we wanted to put it onto the real system. And one of the challenges that our collaborators at NASA Ames that had built the hardware, it actually was a report requirement for their managers, was to show that their hardware was able to go uphill. And my postdoc at the time, David Surovic, He's actually trained the, used guided policy search and with a planners to bootstrap on this terrain, which is 25 degrees upslope and very rough terrain, to come up with a controller that would be able to achieve going uphill. And then this controller actually worked on the real, sorry, I think I jumped forward. Don't know if I have control over, sorry, it's going to run again. So this controller actually worked on the real system, so hopefully we'll see it again when it goes up. But I have to tell you, this was great success. It made our NASA collaborators very, very happy. They were able to come up with a demonstration for their hardware. It took 6 months for David to actually tune the simulation enough. And he was in New Jersey. The collaborators was at NASA Ames. He was tuning the simulation. He was sending a trajectory to them. They were running an experiment, a week afterwards. They were getting data back. He was observing the video of the real system and of his simulator, and he was saying, okay, I'll tune the simulator now a little bit so that eventually we achieved the transfer. But yeah, and this is an example of the real experiment on the physical platform. Notice that it is not 25 degrees slope, it's 15 degrees slope, and definitely not as rough as we did in simulation. But we needed to get into kind of more complex environment in simulation so that it transfers onto the real system. And the behavior is actually that the platform needs to kind of reduce the center of mass and kind of crawl up onto the slope. And again, information here comes from the IMUs that are inside the rods. By the way, the height of this platform is about, it's as tall as I am. So it's a kind of a big system. There is this slippage that happens onto the ground. Interestingly, the rough terrain in simulation gives you a lot of areas where your end caps, you can actually, kind of use them to climb up, which they do not exist on the real system. But when we're training without kind of rough terrain, we're not getting good transfer. And you'll see here why NASA also likes this system. At the end of the experiment, our collaborator Massimo will come and just throw the Tensegrity down. But you don't care, it's a compliant system, it's gonna be fine, and then you can run another experiment. So it was great success that we came up with a behavior for this system that was executed eventually, but it was a lot of pain, right, to do the training. So our focus since then with the PhD student that was starting at the time and now just finished was, can we come up with simulation tools that we can train with just few examples from the real system. Then we can train the RL inside the simulator and then put it back into the real platform. And we went the direction of differentiable engines using some ideas, with dynamic interaction graphs, I think, going back to some work that you did, Russ. And we were trying to come up with differentiable engines that were still using some first principles from physics and not just put like a neural network at the center of the differentiable engine so as to reduce the data requirements. So we have here kind of components that tells us, I have a parameter corresponding to the stiffness of my cable. I have friction parameters for the end caps and the ground. I'm trying to figure out these values so as to make good predictions and train it directly from data. Now, one of the issues when we tried to move how to use real data in order to train this engine is that we have to run the engine at high frequency to make kind of consistent estimates. 1,000 hertz actually is the frequency that we are running them. But when we get some real observations of the platform in order to train it, you may get something like 10 hertz observations of where the system is. And some of these observations are not where perhaps the contact is even happening, the critical contact. So how do you kind of define the loss here? So yeah, we need kind of an approach that we're only going to be using loss when actually we have observations, but you have to make sure that you are propagating good enough gradient during this process to train the differentiable engine. So the integration scheme was very critical so that the gradient actually goes back correctly. We also kind of use a curriculum learning approach where we first try to show demonstrations without contact. So take the tensegrity and just kind of move it in the air. So learn something about the cables. Then perform some examples that have contacts, then learn something about the contact parameters, and then try to learn locomotion policies and execute them onto the real system. So here you see a sim-to-sim example. On the left side, it's Mujoko, where we trained a policy on the ground truth Mujoko system. And on the right-hand side, we actually first tuned our differentiable engine to the output of Mujoko, learned the policy in the differentiable engine, and then executed it back to Mujoko. So in terms of data points that we used from the ground truth system, learning the policy directly on the system requires about 100,000 propagations of the system. But we can actually get, we can train the differentiable engine only with 1% of such propagations of the real engine, right? So about 100 times less effort with the real system, in this case it was a simulator, but the ground truth system, in order to tune the engine and then train the controller there and then push it back to the real system. And together with our collaborators, again at Yale, for some reason I'm collaborating with mechanical engineers at Yale all the time. So Rebecca Kramer-Botillo, she's working on soft robotics. So she built, and her group, a 3-bar Tensegrity as part of our collaboration. And they're very interested in soft material. And they have come up also with these shape memory alloy cables, which are able to also report to you their length. So we're getting some additional information here from the cables, how long the cable is. So you see here a trajectory which was actually manually developed by Rebecca's students, Will and Sean, that we use. Then we use our perception tools from Rutgers to actually track the pose of the rigid rods. And this became our training example on how to tune our engine. So we tuned our engine so the output for this trajectory is the same in the real world and in our engine. And then we tried to train in our simulation a more complex trajectory. And that's a recent result. We only achieved it 2 weeks before the ICRA deadline, so we declared victory and submitted the paper at ICRA, where we actually now able to take the control that we learned on the identified engine and execute it onto the real robot. And you see here, this is going to be kind of a curved trajectory. And you see as well the simulation prediction for the same set of controls, right? And this is the identified engine. And this is an example of what Ken Goldberg calls real to sim to real. We got some information about the real system. We tuned our simulation, and then we transferred it back to the real system. And now we want to keep applying this, right? I put so this is real to sim to real, star. Hopefully, we can keep iterating and keep making our predictions better about our simulation. Perhaps in the vicinity of a specific trajectory that you're executing, you tune your simulation around it, and it's very good prediction now for that specific trajectory, which you can then use to compose different trajectories for more complex behaviors. Okay, so I just want to kind of conclude some of the messages from the things that I said. Compliance is good at the hardware level. It's something that helps us, to reduce kind of the effort that we had to put on the AI of the system. So some of the intelligence can be mechanical in nature. At the same time, it introduces some challenges in terms of the predictability of your robotic system. And some of the ways that we should address that is, tighter integration, tighter loops in terms of fast updates from perception and kind of fallback plans as well from the planning side. We have to be able to figure out when we should explore, when we do not believe that we have enough information. Some of other work that I'm not going to describe here today is in the area of mechanical search. What if I want to retrieve an object and I don't see everything right now? How do I reason about what perception tells me is not answering yet my problem, and I need to change the world so as to be able to answer it? And I'm a big supporter of introducing data-driven methods and machine learning approaches, as components perhaps of an entire more classical system where I will still perceive the world, perhaps in the context of manipulation, I will still perceive objects. Thinking about objects helps us as well to interact as well with, with people and get task specifications. Then coming up with planning operations over them, and then executing them. And perhaps at the control level, we may need as well to benefit from kind of RL strategies that learn the right behaviors, that are policies that are robust, where we bootstrap them in simulation as long as we build an accurate enough model. And hopefully, we help them to generalize in new setups. Well, thank you. I'm running a little bit late, and thanks to all my students, my collaborators.
Okay, any questions? I'll start with one I had. So we talked about perception, we talked about dynamics. You've got such a rich history in planning and control. So do the limitations of perception reduce the importance of planning, or what is the role of the type of planning that you started with have in the manipulation systems that you're seeing in the problems you're trying there and the problems you're seeing at Amazon?
Yeah, so I got into perception because I want to do planning, and if I don't know the scene, I cannot do planning. And there is this issue that the output of the perception is noisy. So some of our approaches that we have taken as a community is that perhaps I can do belief space planning under uncertainty, where I'm going to try to come up with the uncertainty of the objects and then react to it and come with robust solutions. And we've done as well this work. Definitely, there are way better experts here than me in this area. My current impression is that it's a difficult path to make progress with. We are not good at coming up with uncertainty estimates about our, how off our estimation is. It's a very slow, typically, solution. So kind of being much more reactive, more on the replanning side of things, and saying, having a way of estimating whether I know enough that I can reliably plan given the information I have available. And if I don't believe that I have enough information, switch mode to instead of solving my problem, collecting the information so as to be able then to plan. But planning is still there in both cases, right? How I believe I have enough information, I'm going to plan towards my task, given the partial information I have about the world, and be safe about the things that I do not know yet. And if I have to do exploration, it's a planning problem still of how do I maximize information given.
But how do you maximize information if you don't carry the belief state representation? Do you have heuristics for that?
I think in many situations, it's like I know, I don't know, so I just need to increase the space, the subset of the state space that I know about.
Yeah. Other questions? All right. Furthest possible person.
Hi, Professor. Thank you for an interesting talk. I'm curious about the real to sim to real work. The question I was going to ask you is, how do you know if the initial training data from the real world is rich enough to use it? But you mentioned that the idea is to keep training the simulator. So I'm curious, how long does the simulator take to tune? Is it reasonable to actually implement that? Like, is it a matter of seconds or minutes, or does it take hours to fine tune?
Yeah, so I kind of tell to my students this project, Kun, don't try to downgrade as much as possible in your paper the computation time for the simulation, because the point is that the painful part is the real world experiment. For this experiment here, it was in the order of about 20 to 30 minutes that the engine had to kind of, both in terms of training the engine to kind of match the output, because the system identification side, and about that much if you want to do RL to train a controller. Specifically for the 3-bar Tensegrity, we actually did not even do RL. We did kind of like optimization. So that was even faster in terms of coming up with the control. But the RL for the 6-bar Tensegrity was still in the order of some tens of minutes per behavior.
Thank you so much for your talk. I just wanted to take your thoughts on what are your thoughts on like cost function tuning, and how do you optimize that in your case? Especially, I like your example of the NASA one, which was taking the thing.
So cost function in terms of like the RL strategy. So yeah, everybody likes RL because it's going to take the engineer out of the equation, and then the engineer has to tune the reward function, right? And that's where a lot of the magic lies in this case. And David, who did the work, yeah, he had to do a lot of engineering of detecting the right reward function. Thinking, and it comes down basically to whether the center of mass makes progress. You define the task as a trajectory for the center of mass that you want to move towards. Like perhaps I want to follow a zigzag path, so I have to go through these configurations. And you measure how much progress you are making along this trajectory, together with some information about your contacts on the ground, and if you maintain the right contacts that will allow you the right type of transitions towards these directions. But that was, again, manual engineering of how to make the RL to work given this cost function.
Okay, last question.
Thank you for the great presentation first. And I'm curious how these data-driven post-tracking methods you have introduced, what are their failure cases? Do you have any take about like when would this method fail? Like if I take this method and try to use it in our own room, maybe we turn off the lights, maybe we put a very weird background, and would this method still work? Or like in what case it would fail?
Yeah, so the input on the first part of this pipeline, for instance, in bundle track, it's doing a segmentation of the mass corresponding to the object, and then feature extraction. Yeah, you can. So either of those two can go wrong, right? You could be moving things very fast, and perhaps this influences the segmentation output for where you believe that the object is. At the same time, I'm also honestly surprised by the quality of segmentation of some of the pre-trained models. You know, they come from the big companies. They have trained on so much data that they seem to have been doing, relatively well. Although I think it's still interesting to be working in the area of segmentation. And the other thing is, you have again the textureless objects, few features, difficult to do matching. I really like the second part that is not neural network. I believe this is a really good thing we should be doing in the context of manipulation and reconstruction of objects, similar to what the SLAM community has been doing. How to put everything kind of together. Some of the questions there is how do you make an intelligent detection of which previous frames should participate in the post-graph optimization for the last, for the current viewpoint. But I think the failure modes on the first part are kind of the failure modes of segmentation and feature extraction.
Thank you very much for the talk. Yeah.
Okay, thank you all.